Hello everyone, I am Bradley Sward, Associate Professor of Computer and Information Science at the College of DuPage in Glen Ellen, Illinois. And this video today is going to look at 5 different implementations of arrays, and so 5 different word problems. If you're in my class, then you've seen them in my activities. You've only seen one of them, but I figure I'll go through all 5 because it doesn't hurt to have as much practice with arrays and indexing and elements and all that kind of cool stuff as we can. So let's take a look at the first problem. And one thing to note here, I've already created a print array function, and I've already done this in previous videos, so I don't think it's too much of a stretch just to kind of throw it in there. So I need to pass in a pointer to an array, and I need to pass in the size of the array, and it will just go from 0 to size -1, printing out all the elements with a space separated, and then when that's all said and done, then just put an end line. And so I've set everything up here. I just set up an array size of 8, and I print out this array, and this is what I get. Of course, the values should look the same on the printout as they do here in the array in my code, and they do. So I know my function is working pretty well here, and I'm kind of already ready to start the activities of this problem. So I want to develop a C++ function to find the number of even and the number of odd integers in a given array of integers. So if we go through here, how many evens are there? There's 1, 2, 3 evens, and there are 1, 2, 3, 4, 5 odds. So I wanted to make sure I did something that was, you could tell there was a difference. So I want to pass in the array, pass in the size of the array. We already kind of know how to do that. And then pass in 2 other parameters for the reference parameters for the number of even values and the number of odd values, and the function doesn't return anything at all. So what I would like to be able to do, just to say before we write the function, what I would like to be able to do is keep track of something called evens and say, okay, there's an odds, keep track of it over here. And just understand that this is not this isn't a common way we would do something like this. This is more of a chapter 11 or chapter 13 problem. If you wanted to do this the exact 100% right way, this is a good example of just testing out reference parameters and a few arrays and other odds and ends. Evens and odds, right? Odds and ends. But this is a good example of just trying things out. So I have evens, I have odds, and I would like to be able to call this function, and I'm going to call it number of evens and odds, I guess. I can say in, and then I can pass in the array. I can say it's A. The size is array size, because you already see that above there. That's how I passed it along before. And then I want to pass in the number of evens and the number of odds. And if this function works right, when it comes back, number of even values will be evens. And then the number of odd values will be odd, of course. There we go. And then, so that's how I would like to be able to use this. And so let's try it out. Let's do what we need to do here. So I'm going to steal this guy. Well, I'm going to borrow this part so I don't have to type it out again. And we said it doesn't return anything, so it's a void function. There's nothing to, there's nothing to say int f equals, because the return type doesn't match, because int won't match the void that we're trying to do. So come back here. So the void function is called number of evens and odds in, and we're passing in an integer array. I'll just call it A. We're passing in its size, and we're passing, and I'm just gonna, let me just do it wrong here just for a second here. Int size, and then we'll say int evens and int odds. Maybe you already know why I did things, but let me just go through it. So what am I doing? I'm kind of doing what I did before. I'm going through every element one by one by one by one by one. So I'm going to go for int I for index is equal to 0, because everything is 0 base when it comes to the array. Everything up to but not including size. So that'll handle every element, every legal element in that array, plus I. And as you might imagine here, if I take A at the I location, which is an integer, and I mod it with 2, and I get a 0 then what that means is I divided by 2 and I got a 0 remainder. And it was evenly divisible. 2 went into whatever number evenly with no remainder. That means it's an even number. Plus plus evens. Otherwise, else, plus plus odds. I don't have to do any extra work. If this number is not a 0, it has to be a 1, which would mean that it has to be an odd number, whatever value is stored in this memory location here, and I'll just increase it. So, okay, so let me run this now. And we were talking a minute ago, we would expect to come out 3 even values and 5 odd values. But what we get is this. We get 0 even values and 0 odd values. And what's weird is if I hit a breakpoint there after the for loop completes, there are 3 evens. There are 5 odds. So why does it, when I go back here and I print all this out, how come it prints 0 and 0? And so remember back to chapter 6. Oh, it was probably in the back of the lecture, but it's so important. The difference between pass by value and pass by reference. And that was the one thing that I neglected here. When we did things this way, I made a copy of the variable over here on the main side, and I passed the copy along to this function. So as you saw there, everything updated properly, but it was the copy that was getting updated, not the master value that's stored here in main. And so that was where the problem came from. So when I come back here, the master copy was never modified, and evens was 0, odds was 0, so that's what it prints. So that's a big deal. I mean, a lot of times we want copies, but sometimes like in this case, we want to be able to increment that value and increment this value. And what that means is instead of passing a copy along this time, this passes basically, a reference, or it basically passes the original data along, no copy, to this function. And so instead of modifying a copy, it modifies the data that is coming from main. And now you can see, if I get this, there we go. There are 3 even values and 5 odd values. That one little ampersand, and my advanced C++ students can tell you that, and within the last week or so on their first exam, missing those little ampersands made a program that should run in maybe 20 to 30 seconds, made it run in many, many minutes, because they were passing copies of things versus passing references and not making copies of things. And it's just, that's a huge difference. Remember this. Remember this always when it comes to that. Anything larger than ints, we almost always pass by reference, and then we pass by const reference if we want it on a read-only basis. But we are modifying them here. We're modifying evens, we're modifying odds, so we don't have to worry about that. Okay, so that pretty much covers the first problem. And so now we're ready to move on to number 2. All right, so our second problem here, develop a function that rotates all of the elements of an array 1 to the right. So like in this case, 4, 7, 9, whatever, the 3 should come around and everything else should shift over in the array 1 spot. So all we should do is pass the array, pass the size of the array, and then all the magic should happen in that function. We don't need to, since we're passing a pointer, basically an array, which means we're passing a pointer, we don't have to worry about passing anything more, but we do need to know how many elements we're going to be shifting around. So, okay, so let's get to it. All right, so let's see. So what I would want to do is have this and say print array, and then I want to say rotate array. And then I want to print it again. And of course, I don't have the function developed yet. That's why it's screaming out red. So it's a void function called rotate array. I'm going to pass in an int array, I call it A. And I'm going to pass in its size, like this. And then all the magic's going to happen. And so right now it will work. Nothing's going to get done in here. But it will work. And there everything is. So I'm happy with that. I have a compilable, runnable program at the moment. And so now, if we think about this, how many movements do we have to make? We have to move everything over 1 time. So we have to make 8, in this case, since we have an array size of 8, we have to make 8 movements. And so, okay, so we basically have to do this. So I equals 0. I is less than size, plus I. And so what we want to do here, let's just try it out. This isn't going to work fully, but it'll work most of the time here. What if I say something like this? A of I plus 1 equals A of I. So take the 0th element and move it into the first element. Let's just see what happens. Whoops. Okay, 4, 4, 4, 4, 4, 4, 4. Because I copied it over to here, which means then I copied it over to there. No, it's not what I want to do. Obviously not, right? Whoops, and it crashes later on because I even went outside the bounds of the array. Because even by going I and adding 1, I get outside the bounds. So we'll have to fix that. So what else? Oops, let me close this down here. So, okay, that didn't work. So let's see here. So instead of starting from the front, what if we started from the back? We can say, okay, let's start from size minus 1. Because if you remember, if we're doing 0 count, that the size element is going to be 1 past the actual array. So we have to start back size minus 1 as long as the I value is greater than 0. And this time we're going to subtract off. And this, what happens now if I say A of I is equal to A of I minus 1. Now what happens? Now what do I get out of this? And now you can see we're getting closer. Everything is shifted to the right. The 2, the 1, the 5, the 6, the 9, the 7, and the 4. So the only thing that hasn't made its way around is this 3. It needs to get all the way back to the front. And we can do that by just saving, I'll call it the last, just last for last value. It's equal to A of size minus 1. And then right here at the end, you say, oh, A of 0 is going to equal last when it's all said and done. There's no, there's no truly easy, maybe there's an easier way, but I'm not thinking of it right here and right now. But now you can see that everything has been shifted over. The 7, the 9, the 4, the 7, the 9, the 6, 5, 1, 2, and then the 3 has worked its way around. I think that's pretty cool. So that's how I would do something like that. And again, it works for almost any size. Anything size of, well, yeah. We'd have to test this. If we could put a, what would happen? What would happen if I put a 1 in there, right? Would it crash? Let's find out. No, it seems to make it through. Okay, so pretty much every array, what if it was 0 sized, right? That's when we'd have problems, because then this would do some weird stuff. Because we would say, what's A of -1? This isn't Python. There is no -1 in C++. So we would be outside the bounds and we would be doing bad things. So we probably just want to make sure, just to make sure, if the size is greater than 0, do this. We don't always have to worry, we don't always have to worry about all these fringe cases, but in this case it is a big deal. If it is possible to send like a null pointer or something like that, an array that has no size, as weird as that sounds. But in this case, yeah, I think this makes it rotates everything and it does everything like it's supposed to. So, okay, so problem 2 solved. Let's move on. 3 and 4 are going to be pretty much the same. Alrighty, so our next problem is as such. Develop a C++ function to rearrange an array so that all the positive elements are going to be on the left-hand side and all the negative elements are going to be on the right-hand side. So we don't know how many positives, we don't know how many negatives, we don't know the size. There's a lot of things going on here. But we do know we want to pass in the integer, pass in the size. It doesn't do anything, it doesn't return anything. All the hard work goes in here. And when this is all said and done, all the negative values will go over, not sorted or anything. We're not sorting. So it should go in order of -2, the -3, the -5, the -1 on the left, and then 4, 9, 6, 5, 4 on the right when it's all said and done. So let's see. And if we can do this one, we can do the next one because it's just a variation of the same thing. So I say, what is the index? What is the swap index? Because I'm going to need to swap, but I'm going to start with the 0 location again because right now, like this, there's like a pivot point. Like there's going to be a position somewhere in here where there's going to be a negative value, negative value, negative value, and then you're going to go, oh, now we're going to move over to the positives. And so that's this swap index. It's our pivot. I'll call it pivot. That's a cooler name. And we use it in more complicated sorting algorithms and things like that. So I have this working for me. So I say, so if I find a negative value, it should go into the 0 position, and we should just swap it. Kind of swap it out. And let's just see what happens. If I just go ahead through here, and I say, okay, I have my pivot position, and I say, okay, oops, a for loop here. Start at the 0 location, go up to size, but not including, as always. Go in here, and say, okay, if the value is, okay, I just want to make sure I do this right here. Put all the positive elements to the left. So if a at the I element is greater than or equal to 0, because 0 is a positive value in computer science, then let's try swapping whatever is at the pivot position with whatever's at the I location, and then, if that's the case, increase the pivot point. So because we're trying to move over 1. Let's just see what happens. Let's see what that does. And it might work, but I might have missed something. Let's see. I developed a function to arrange an array so that all the positive elements appear to the left. Apparently, when I spoke earlier, I was thinking all the negatives go to the left. But you see that everything, not everything kept its order. 4, 9, 6, 5, 4. All the positives kept their order, but not necessarily all the negatives kept their order. And that wasn't part of the stipulation. That wasn't a rule here that I keep the relative order. So, and that's called stability when it comes to moving and transforming and moving stuff around inside arrays and vectors and data structures. But that wasn't a requirement. But I did do the job. Everything that's positive is on the left-hand side of everything that's negative. So now I guess my only question is, what happens if everything is negative? Does it crash or does it work? Because I'm curious. Negative, negative. Oh, you're not allowed to do that. That's okay. And so now if everything is negative, nothing should change, or at least, yeah, nothing is really, everything's pivoting. And then what happens if everything is positive? And if you can handle those cases where everything is positive, everything is negative, and then and then you did something in between, you basically are handling all the cases. And it doesn't seem like it's crashing. So that seemed to be it. Keep track of where would you put, if you had to move a value to the left-hand side, where would you move it? I would move it to the 0 location until I put something there. Then I got to put it in the first, element 1, then element 2, and so forth and so on. That's the whole idea here. And so for problem 4, it was basically the same idea, except evens and odds. So right here, this is the only thing you would really need to change. If I was, to change this into even and odd, say mod 2, all the evens will go to the left and all the odds will go to the right. So 4, 2, 6, 4, and then all the odds are, all the evens are here, all the odds are to the right. So with this, you basically kind of have what you need here. And what's cool is this is definitely more of an advanced thing. We could stipulate what this function is. Like we don't have to write a new function every time we want to do this. We could supply a function parameter here that would do this work, that would return a true false. Because basically when we're doing this kind of transform, there's either 2 ways this thing can go. It can go to the left side or it can go to the right side. So as long as whatever we would put in here returns a bool, if we've set up this with a function, as long as that function returns a bool, then it will work. And whatever it is we do, we could swap and we could transform. And that's the whole idea behind like the standard template library the transform function and those kind of things. It's, you know, like if you want more information on that, look into the Jasudis C++ book, the C++ standard library book, if you're interested in that. It's pretty cool how you can architect this so we don't have to write a new function every single time we want to try things that are different. All right, so the last problem is take an array, and in this case like this, take an array and tell me if it is sorted low to high. That's the last thing. I'm just gonna talk because I remember what it is. So just tell me, bool is sorted low to high. Okay, and I say I'm gonna pass in the array again, like always, pass in the size. And so the thought process for this is I'm gonna look element to element, and I'm just gonna go, hey, is the first element smaller than the second? And the answer is yes. Then I'm going to keep on going. Hey, is the second element smaller than the third? And then the third smaller than the fourth? And if I can get through the whole way without finding a false statement in there, then I go, yeah, I'm going to return true because it's sorted. So something like that, bool sorted equals is sorted low to high. But if I find one counterexample, then no, the whole thing is busted. So what I want to do here, I want to check, I want to go through this with a for loop, say, okay, I'm going to start at index 1, and I'm going to go as up to, but not including size, plus I. Yes, I'm starting at 1 this time, because what I can say here is if A at the I location is greater than A at the I plus 1 location, no, I'm sorry. If A at the I position is less than A at the I minus 1, because I already talked myself into confusion starting at I equals 1 here. So if A at the 1 location is less than A at the 0 location, I'm going to return false. I found a counterexample. And it's just going to keep on going, keep on going. And the reason I don't have to worry about the off by 1 here, why don't I have to worry about size minus 1 or anything like that, is it's already accounted for because I'm starting at 1 and 0, 2 and 1, 3 and whatever, and I'm never going to have to worry about hitting this size and going outside the bounds of my array if I do things this way. So what's cool here, what I can do is something like this. Watch this. This is pretty cool. While is sorted low to high equals false. Okay. What I want to do then, I'm going to pick 2 elements. I'm going to go like this. I'm going to say swap, and I'm going to say A at rand mod array size. And I'm going to do it again. Just give me a second here. Make sure all the errors go away. So what this is going to do, this basically is saying here, print the original array like this, and then just, we call it, this is like the worst sorting algorithm ever. It's called bogosort. And it's basically saying, okay, if it's not sorted, pick 2 random elements. Just pick, they could be the same one, whatever. Swap the contents, and print, and then check again. Just it's the random sort. It's the bogosort. But this thing will go, oh my god, how many elements are there? 10 elements? Oh boy. But that's the fun of this. I'll bring this down a notch or 2 if it doesn't solve itself in a period of time. Let's see, how many? I have 9 elements. What is 9 factorial? Okay, Google, what is 9 factorial? Okay, so about 300 something. I forgot the number already. But 9 factorial means there's 360,000 different ways that this thing can be organized. And it's going super slow because the print is the slowest thing ever, because it's just the way it goes. So it's going and printing and random, and just every time you can see it's swapping 2 of the elements. This one and this one, just randomly swapping. And then going, hey, are you okay? Are you sorted? Are you sorted? And what can make this faster is if I get rid of this print array here and bring it down here. And I only print it when it finishes up. And there you go. So yes, again, that print statement is the slowest thing ever, but it swaps and it swaps and it swaps and it swaps, and then at the end goes, oh, okay, 1 is less than 2, 2 is less than 3, 3 is less than 4, 4 and the equality is okay, so but 4 is less than 5, and 5 and 5 are okay, 5 and 6, 6 and 9. We've gone through the whole thing. We didn't find a counterexample of one of the values being larger, the one on the left being larger than the one on the right. So therefore, we made it through with no counterexample. The thing must be sorted. And so that is, so we kind of say, so taking this away from, and we made this pretty cool because we basically created a sorting algorithm. But like I said, the best sorting algorithms are O of n log n. The ones we're teaching you in this class are O of n squared. Those are horrible. And this one is O of n factorial. Because, as I was saying, there's 9 factorial different ways that we can do this. And there's no rhyme or reason. We're just randomly picking things. The thing could be one swap away, but we wouldn't even know. And then if we randomly pick a different one, now we're 2 away. And it just kind of comes and goes and comes and goes. Now the question is, how many different sorts did it try before it said, oh, I found it. Are you interested? I'm interested. It's computer science stuff, right? Oh, swaps needed. You know what I mean. But I already did it, so no, I'll change it. I'm horrendous at naming. Okay, so let's see. How many swaps did it need to get itself to the answer? Oops, what did I do wrong? Oh, that in. Okay. So now it only needed 202,000 swaps. Yeah, right. Those of you just wait, chapter 8 stuff this week or next. Like, yeah, that's horrendous. And what happens if I make this 10? This is the factorial part of this. Only 466,000. I got lucky. But how about I up it to 13? They had 3 more. And this is where we're starting. You can start seeing we're getting into problems. Even with my computer running nonstop, not printing anything, as I'm talking, it's not solving it. And the thing is, like, even, like, we're reaching about the limits, 13 factorial. This is a huge, every time you're multiplying by a larger and larger number. So, like, if you wanted to sort 50 numbers, you might have to wait until the end of time. And I'm not even kidding. Like, the end of time is when it might sort 50 numbers or 100 numbers or like 1,000 numbers, 1,000 factorial. You can absolutely forget it. And so, yes, it's the absolute worst sorting algorithm because we should be able to sort 1,000 things in a simple and in an amount of time. Oh my God, how much is that? Let's see, 100 million swaps were needed to sort 13 things. That's ridiculous, right? So, but it did sort it, or it did make sure it was sorted, and so my function is working properly. So if it's 100 million now, then it should take about 700 million if I make it 14. But again, since it's random, and if you have a large enough number of things that you don't want to sort, or if you're testing against, there's a chance it might never do it. Because the probabilities, I guess if you give it infinite time, yeah, it'll do it. But if you're expecting it in a reasonable amount of time, this is not the way to go. And that's why a lot of research was done in the 50s and 60s, trying to figure out the most efficient way to sort and to search for data. We found 3 searches. We found a ton of different sorts. But pretty much the quick sort is, in most cases, the best way to go. All right, so that covers 5 examples. Hope you guys enjoyed the video, and I hope you learned quite a bit about this, about arrays and just algorithms of accessing arrays and so forth and so on. So it's very possible I misspoke while I was doing all the things, thinking and talking and doing and all that stuff. So please comment below here on YouTube or email me at swardb@cod.edu. So let's see, definitely moving on to bigger and better things. So Arrays are a big part. Collections of data is absolutely everything a computer is built to do. So this is a good chance to get those skills honed before we move on to those bigger and better things. So hope you guys have a great day. Hope you have a great week. Hope to see you in the next video. Take care. We'll see you then.